Right. So now we come to the interesting part of the lecture, not the other details, but the content itself. So by the end of this lecture, you'll be able to identify what is thermodynamics, and we'll be able to explain it in simple and direct language to another person who don't know about this. And then you'll be able to define what is system and what is surroundings, then a closed system, open system, and isolated system. You'll be able to understand the differences between these three systems. Then extensive and intensive properties. What are these terms stand for? I believe you already know the properties, but what are these extensive and intensive properties? So we'll be discussing about that as well. Equilibrium state, quasi-equilibrium process, and cycle. So what are these terms stand for in the sense of thermodynamics? Density, specific volume, pressure, and temperature. How these things are related and how we can use these in thermodynamic analysis, we'll be discussing in today's lecture. So importantly, the recommended text for this course is Fundamentals of Thermodynamics. I'm using the 9th edition of this book, but at the same time, I believe there are some, or if you have an older version, you can use that as well. It would not affect your performance. So if you already have, let's say, an older version, I don't want you to buy a new book just for this course. Okay. Okay. So thermodynamics initiated from two Greek words. The first one is therme, and then it means heat, right? And dynamics is power or force. So you can say the study of thermodynamics as heat force or heat power, right? So when you put heat and power together, it doesn't look sensible. I mean, heat power, it doesn't make much of sense, but heat force, you can get the idea. Like the definition says, study of energy relationship that involve heat and work. Basically, we are trying to study how we can use heat and work in combination in this course, right? So I want you all to try what's shown here, like try to rub your hands together. I'm pretty sure you have done this in a winter day. So once you start doing this, what can you feel? What do you feel? What's the sensation? You can put your answers in the chat or you can speak. Excellent. So all of you are answering it great. Perfect. So once we start rubbing our hands against each other, like we create, due to friction, we create heat, right? So now we can essentially interpret this process as we did some work, right? We moved our hands so that we generated heat. So can heat be used to produce work? So we use work to produce heat. Can heat be used to produce work? Awesome. So we can definitely use heat to produce work, and in the coming sections, we'll discuss how we can use heat to produce work. Okay. Okay. So we can see how we like some mechanisms where we use heat to produce work, right? So in the left-hand corner, you can see there's a cannon or a pistol as well. So there we burn gunpowder and we start propelling our bullet, right? So that it can go to a certain distance. That is like we created heat, so that heat energy was converted to work, and then we used it as a gun or a cannon, right? And in the middle of the slide, you can see here. So this is a James Watt's heat engine, and there what we do is we have a boiler and we heat it up with fire so that we can generate steam. Once we created enough steam, we open valve 1. When we open valve 1, then the chamber is getting filled with steam. So as you can assume, when the steam fills up, this piston should be pushed upwards. When we push this piston upwards, then this end of this beam goes down, right? so which essentially can be used to do some useful work. So this can be connected to a pump or some other device. When we connect this to a pump, then this energy can be used to pump water. So after this piston receives the top of this cylinder, we can close valve 1 and we can open valve 2. When we open valve 2, this is a condenser, so it doesn't have any steam. So this steam flows down to this condenser. So basically, this end of this beam comes down, and with that, this end goes up. So basically, you can get a motion like this, right? So with that one, you can pump water, and this is around 1840, if I'm not mistaken. Don't misinterpret this one. It is not the first steam engine in my understanding. It's one of the most efficient ones which were popular during that time. Okay, so we can define a heat engine, like a device that produce a heat engine is any continuous operating device that produce work through the transfer of heat from a high temperature body to a low temperature body. Okay, so this is a heat engine, James Watt's heat engine, it says, right? So we can generally represent any heat engine using this schematic that you see in your right hand corner. So basically what a heat engine does is it absorbs heat from a heat source. When we have a high temperature body in the process, we call it heat source because it can give away heat, right? And then our heat engine absorbs heat from this high temperature source or high temperature heat source, and then produce some work, which is indicated here, and then eject some of the heat into heat sink in the bottom, right? Heat in the bottom to the heat sink. So this is the basic idea of a heat engine. So any heat engine, any device that fall under this definition that you see in the top of the slide can be represented as this, as you see in your right hand side corner. Okay, and thermodynamics is not only about heat engines, it can be used for multiple purposes. If you take the left topmost figure, this shows a residential HVAC system. So residential HVAC systems means heating, ventilation, and air conditioning systems, right? So I'm pretty sure all of you use these facilities. If we have a hot water tank, you can use thermodynamics to analyze how this hot water tank perform. If you have a space heater, then you can evaluate this space heater's efficiency and performance using thermodynamics principles. And at the same time, if you have an air conditioner, then you can use these principles to evaluate the performance of air conditioning. Even to evaluate the building as a whole, the building energy performance, we can use thermodynamics. Actually, like, we will not be analyzing building energy performance in this particular course, but down in the road, you can build upon this series and you can use building energy simulation softwares and other related principles, tools, and everything to evaluate the buildings. And the knowledge for that will be building upon this course. And if you look at the lower left corner, this is a coal power plant. So coal power plants use Rankine cycles to get the steam energy and convert it to power. So you can use the basic thermodynamics that you learn here to evaluate the efficiencies, and depending or developing on that, you can use that knowledge to design and evaluate the performance of these kind of devices. So hydropower systems and like other hybrid energy systems, usually when you see solar panels, wind farms, batteries, and everything, so you don't feel like it's exactly thermodynamics, but you can use the thermodynamics principles to evaluate the energy balances of different systems, such as if you want to see whether we provide enough energy for a given building using our power system, then you can use the first law of thermodynamics to see the energy balance of the system and therefore design it in one way to help design the system, right? And this fourth picture is a gas turbine. In any aircraft, like you have some kind of a propeller machine, so like some kind of an engine, right? A gas turbine is one of the common engines that we see in aircrafts, and in this course we'll be evaluating the efficiencies and operational conditions of gas turbines using basic thermodynamics. And this is not enough to design a gas turbine, but we can check the theoretical limits and we can say, okay, this will be the maximum that we can get. And it's very important we do that, because if we are to prototype a device and then see, okay, this is not working, that is costly. Even with the simulation tools, like some CFD tools can be used to design turbo machines, but still it will be costly if we just jump in and go there and design the whole thing in a software tool even, and then say, okay, this design was wrong and we should have done it in a different manner. And the right hand side, like the train that you see, is a steam and has a steam engine, and we don't use these in the present as much, but it was very popular back in the day. So in a steam engine we can use thermodynamics to evaluate the performance, efficiencies, and the condition of steam and steam water mixtures coming in and going out, right? In addition to these, I'm pretty sure like most of you are interested in racing cars and your day-to-day driving cars and everything, the cars basically, right? Every car other than the electric ones have an IC engine, internal combustion engine. So one of your friends who's like working with the cars may come to you and say, okay, I developed 100% efficient car, right? And maybe he or she will put it this way, okay, no, just to make it so realistic, I developed an IC engine, or my car works at 90% efficiency. If it is an IC engine, and if you have taken this course, you'll be able to say that, okay, no, it's not possible. 90% is not possible, because in this course, we establish the theoretical limits that an IC engine can go. So it's usually around 40 to 30 to 50% range. So basically somebody says it's like 80, 90. So that is kind of tricky, and you have to see how he or she did that. So you can see this course is not about a bunch of boring equations. This course is about some cool stuff you can really use to understand some of the physical things that you see around. So I really request you to be engaged in the course, ask questions, and study the material on the day itself, and don't keep waiting. Okay. Do you have any questions up to that point? Are we all clear? And can you hear me good? And am I speaking too fast or too slow? Anybody? The pace of the lecture? Perfect. Awesome. Thank you very much. And now let's look into laws of thermodynamics, right? So you all know, as a civil society, we operate with civil laws, right? We know what we can do and what we cannot do. And then looking at our laws, somebody can say, okay, this will happen if such a situation occur. If somebody does a criminal activity, then the police will be there, because we know that it's our law, right? So similar to that, our thermodynamic systems have laws of operation. So we can use these laws to interpret or to understand our thermodynamic processes. So there are three main laws. One of these three laws is the zeroth law. So zeroth law discusses about thermal equilibrium, right? So as you can see, if we have three bodies, A, B, and C, right? I'm just showing the same hand, but assume this to be three bodies, A, B, and C. A, B, and C. Okay. So if A and B are in equilibrium, and B and C are in equilibrium, we can say that A and C are in equilibrium. So in other words, um, if A and B are having the same temperatures and B and C are having the same temperatures, then we can see that A and C are having the same temperature, right? So you might think, okay, is this guy crazy or what? Like, why is he telling that when TA equals TB and TB equals TC, that TA equals TC, right? You did these kind of solutions in your high school. Yeah, I understand. Like when we say it that way, like from the mathematical point of view, it's not a very complex law, but when it comes to physical problems, it's very important. Like once we know there are two things in equilibrium and then there's another two things in equilibrium, then to know that these two are in equilibrium. Okay, so this law is called zeroth law, and this will not be one of the main laws that we use continuously throughout this lecture series or this course. So here comes the most important one, the first law of thermodynamics. So we'll be using the first law and second law more frequently compared to the zeroth law. Okay, so it says energy can neither be created nor destroyed. It can only change forms, right? So it's about quantity of energy and conservation of energy. Do you feel this is familiar? Like, have you ever heard this before? Like anybody? Yeah, right. So in high school, energy conservation, I believe like you all have heard this one before. So what we are trying to do is not to teach you the same idea that you learned in the high school, but building on that idea, we are trying to see how we can apply the conservation of energy into thermodynamic systems. So by the end of this course, you will be able to evaluate thermodynamic systems for its using energy conservation, and so that you can quantify the quantities of energy coming in and leaving the system and everything. Okay, so the other law is the second law of thermodynamics. So it's about quality of energy. Okay, now we are getting into a little bit of a tricky area because you don't have the background knowledge about this one. Some of you may have, but I assume generally you may not have this knowledge. But I'll try to explain quality of energy using simple terms. This is not the quality that we are talking in thermodynamics, but you might get a sense of what we are going to talk about. All right. So if we think, okay, if we think of a reservoir, let's say it's mounted on a pole and which is located up somewhere above ground, right? And then we see a reservoir that is located on the ground. So we have A and B, right? So out of A and B, out of the water in A and B, what do you think have more potential to do work, or which can do more work, A or B, if we have same amount of water quantity, right? Perfect, you are nailing it. So it's A, right? We know that it has more potential to do work because it's located in a higher elevation compared to B. So similarly, in thermodynamics, if you think of a fire, let's take a fire, right, of higher temperature and a lower temperature, then what do you think can do more energy, A or B? So like high temperature fire A, low temperature fire B. What do you think, A or B? What can do more work? It's again A, right? Because like it has more energy going on, that's why. So similarly, that's what we are trying to understand in thermodynamics as quality. So in some energy, as we see in this example, the water in B has energy. Definitely, it can do some work, but it is not as high as the potential of the water in A. So that is the difference between quality. In thermodynamic terms, we can say A has high quality energy, B has low quality energy. So this is not exactly the idea of quality in thermodynamics, but I wanted to give you some background so that you can hang on to this idea. All right. So in second law, we say that entropy cannot be destroyed. It is generated spontaneously when a system moves towards equilibrium. Okay. So I'm not going to explain this to you right now. We'll discuss this part in detail in the coming sessions when we discuss entropy. Okay. So the other statement is a natural process always occurs in the direction of decreasing the quality of energy or creating positive entropy generation. So for now, we'll pause about entropy discussion. Rather, we'll try to discuss decreasing the quality of energy. Okay. So if you look at our previous example here, if we pinch a hole, what is likely to happen? To water to go this way, or for water from B to go upwards and enter this tiny hole, A or B, A to B, right? So it is likely to go from the top reservoir to the bottom reservoir. So it always, like, once this water reach B, does it have the same quality or same potential to do work as it had earlier? Right? So that means it always naturally occurs in a way that it reduces the quality of energy, right? And also it says creating positive entropy generation. So if I try to give a bit about bit background about energy, like it's a hypothetical parameter we define to represent the chaos or disorder in a system or in somewhere, right? Let's try to understand this one slightly better in the next statement. In a reversible process, which is ideal case, right, entropy generation is zero. So basically what it says is, if entropy generation is like the disorder, entropy is the disorder or chaos, then if we can do a process in a reversible manner, then the chaos that we create is zero. So let's try to see this one. So reversible process, what does this mean? As the word implies, reversible means once you do it, you can reverse it so that you don't leave any trace. You, let's assume that all of you stand in a straight line in your classroom, right? Hopefully when we open up for physical classes again, not in your houses, but in a real physical classroom. So all of you stand in one line. And then I ask you to take one step ahead, everybody, and remember each and every moment you did while doing it, and then stand one step ahead. And then again I ask you, okay, replicate everything you did while taking the first step, and then take that step back. Okay, so replicate everything means including the sand movements underneath your feet and everything. Okay, so then now you replicated everything. You put the sand particles in the same places it used to be. Let's assume you are very talented, so you came back. Now another person who did not see this process come to the classroom and try to see this one, and I ask this person, do you see, like, whether the students did a step or not? Would that person be able to answer? Like, would that person be able to see a difference occurred by what you did before? No, right? Because you took one step forward and then you took it back while replicating everything the same way, so that there's no difference. So that is the idea of a reversible process. So like, this is, again I reiterate, these examples are to get you a physical sense from what you know, right? This is not a thermodynamic process which we will learn in the coming slides, but for now, like, in a physical process you can understand what is reversible. Okay, So now, again, I'll take another example. Now you stand in one line as previously. And then, so the now I ask you to create chaos inside the class. So you run everywhere, you turn the tables upside down, and there's a paint can, you like splash it everywhere. So like now you have created chaos. And then I request you, please reverse this process so that no track is left, and reverse it the same way you did. So basically, if you pour the paint can like this, like that, backwards, and still the paint should look like the same, and your steps should be the same, sand particles, whatnot. Can you do that? Would you leave would you leave some trace? Any ideas? You would definitely leave some trace, right? Because you cannot exactly like grab the paint from the floor and put it in the can and say that, oh, nothing happened, this is brand new. It's not possible. So that is the idea. Now that is an irreversible process because you created chaos or disorder during the process, so that you cannot replicate the same thing on your way back, right? So that is the meaning, or that is the idea about reversible and irreversible. And what is a reversible and irreversible process in the sense of thermodynamics? Now we'll discuss it in the coming slides. Okay. And the other important aspect, like now we have discussed 3 points, and the fourth point, the other important aspect of the second law, it sets a theoretical limit for a thermodynamic system. So you remember the example I said, some of you, one of your friends drive their car into your carport and say, okay, my car has an IC engine of 100% efficiency. Why he or she cannot claim that? Because we know thermodynamics and we know second law of thermodynamics. According to first law, a 100% efficient car or 100% efficient IC engine is possible. But second law says, no, it's not possible, because it discusses the direction of energy and the theoretical limits of a process, theoretical efficiencies of a process. So the theoretical efficiency, in the sense, it is the maximum you can reach. Using the second law, if we define, okay, this is the maximum efficiency we can reach, you cannot go beyond that. If you modify the process, if it is not a heat engine, then it's possible. Like obviously the electric vehicles can go to efficiency very high, like 90s, 80s, like around that range, but like for IC engine it's not possible. So now you see why we need these laws, right? So the use of these laws. Okay, so now let's try to do this exercise. I know that you have not learned thermodynamics before, but I know that all of you know some kind of meanings to these words. Based upon your knowledge, think how to define a system and its surroundings, right? So please think for 30 seconds and type your answer. What is a system and what is surrounding? Take 30 seconds and do that. So if you are done thinking, you can put up any ideas in chat message. Okay, what is a system? A specific area to study. Uh, thank you, George. I think that's a good way of thinking about it. Any more ideas? Okay, Nolan has an idea. System is a defined collection of bodies or particles and surroundings outside of the defined boundary. Okay, so now you are getting close, and boundary is a good term that we found here. So you say that this a bunch of particles or bodies that we define as system, and then anything outside those is the surrounding. Okay, system is set for, of things working together in parts of mechanism. Yes, so I believe all of these definitions are very close to system in certain contexts, and when it comes to thermodynamics, we have to adapt this idea of system so that we define it for our analysis, right? Why do we need to define a system? For an example, let's say if it is a transmission system, we need to identify what are the parts and how it works and everything. So once we define the system, we know that okay, this is the thing, these are the things that we need to focus on, and anything else, um, anything does not belong to that set of items is surrounding, right? So similarly, we have a way of defining system. Uh, we have a way of defining system use in thermodynamics context. So we'll discuss it in the next slide, right? Um, how does a system and its surrounding interact in the sense of thermodynamics? Try to think from thermodynamics perspective. So we define a system using thermodynamics, and then let's assume this is the system, and anything outside this is surrounding. And then how to define how does these things interact with each other, the system and surroundings? Through heat transfer, that is one way of doing it. And are there any more means of interaction? Yes, excellent. So we can do both. We can exchange heat and work between between the system and surroundings. So either heat can cross the boundary, or the system can do work on the surrounding, or the surrounding can do work on the system. So don't get confused about this, like system does work on the surrounding and whatnot. So we'll discuss these definitions clearly in the coming slides. Okay. Okay. Now, how to define closed, open, and isolated systems? Do you have any idea what it could mean in a thermodynamics context? Closed system. So usually, what do we mean by a closed container? So what is the difference? Closed, no heat exchange, no interaction with the surroundings. Closed, no interaction of mass, interchange of mass. Yes, I believe Desa came closer. So closed, no interchange of mass, and Mena also is closer. Open is, when it is open, there is a transfer. Or when it is open, we can say, to make it better, when it is open, it allows transfers between the surrounding and system. Okay, so think of something closed, and what is the thing that you see? The mass is not allowed to go back and forth, right? So, but it doesn't necessarily say that the heat cannot go in and out, right? A closed container, a closed pop can, or a closed coffee cup, or anything, right? And open, so it allows the mass to go out as well. So like if we take an open bottle filled with water, like if we do it this way, like upside down, then definitely water can go out, right? So that is open. And in isolated systems, so it doesn't allow the mass to go out, and at the same time heat to cross the boundary, right? So that's the three systems. So I'm not going to ask you to write down thermodynamic properties. So like we all know the pressure, temperature, and density, and the mass and everything, these are properties that we already learned in our high school, right? So there are two types: extensive properties and intensive properties. In the coming slides, we will discuss what are extensive properties, what are intensive properties, right? I see that like these concepts could look very simple, right? Because these are not rocket science, obviously. But if you do not understand these concepts very well at this point, then down in the road in the series, you will feel difficulty to understand, right? So I'll share one of my personal experience as a student. Like when I was an undergrad, I used to go to lectures during the first day, like with full energy. Okay, I'm doing it. Thermodynamics, yes, I'm doing it. And then the lecturer or instructor comes and say, okay, now we'll learn about properties. What is intensive property? What is extensive property? And then I feel, okay, these are a bunch of definitions, right? And most of these things are not even difficult to understand. So no, I think like this subject is easy. So I'll take it easy and then I'll go home and sleep. And after 2 or 3 lectures only, I will decide, okay, now I need to go back to the lecture, right? And then once I go there, like then the instructor or teacher telling me things, okay, intensive properties are of this system is that, and extensive are this, and like these properties are there, and these properties are there, and these processes happening. Oh man, like now it is like rocket science, because I did not pay attention to my basics, right? So I know that none of you are like that, but I'm just sharing my personal experience, and please don't be like me, right? Pay attention to the class and learn the basics and build upon that so that you are very comfortable with these terms in the coming lectures, because it is very important. Okay, all right, now let's look into the definition of system. System, a quantity of matter or a region in space chosen for study, right? So all of you like came very close with the quantity of matter. So like when we say like a combination of particles or bodies, like then it says quantity of matter, right? So we can take 1 kilogram of sugar or something like that and then say, okay, this is it, and we are going to evaluate. Or if you take the balloon that you see in your right bottom corner, that you can say, okay, now this balloon, we tie the end of the balloon, so now no air can leave the balloon. We can call this a quantity of matter. The air inside the balloon is what we analyze. Or else we can define the surface of the balloon as the system boundary, right? Then it becomes a region in space, right? And it's very important to note in this one, can the boundary change or not? Can the system boundary, can the region in space change while we are doing analysis? Let's say I got the balloon and I squish it here and there, and like I pull it here and there, and then can the boundary change? It does, right? It change. So you can see when we define a system, it can have a solid boundary as a building that you see here. If you want to analyze the thermodynamic properties of this building or how this building performs with the heating system, cooling system, whatsoever, so we can define outer envelope of this building is this system boundary. So in this case, I have not seen any or many buildings with movable boundaries, right? It's usually fixed. We have walls, so it's fixed. But in certain systems, such as balloon, the boundary is movable. And now, with both these examples, I gave you an impression that we need to have a physical boundary for our system. If we define it as a region in space, then we need to have a physical boundary. Actually, that's very wrong. So we don't need to have a physical boundary. Let's say, if we consider an imaginary box, like a cube kind of space, right? Imaginary cube that contains this balloon, we can do our thermodynamic analysis for this one as well. So in this case, does the volume of our system change when we squish the balloon? Can you answer? Perfect. You are getting it perfectly well. So when we define this cube as our system boundary, it doesn't matter whether we squish the balloon or not. then our system boundary is a different one. Okay, so now you can see we can take a bunch of particles or something and like quantity and say, okay, this is what we are going to analyze, the particles inside the balloon. Or we can say we define we define region in space, right? When we define the region in space, it could be a physical boundary or it could be an imaginary boundary. So depending on what we want to do in our analysis. Okay, so the surroundings is not as hard to understand. Surrounding is the mass or region outside the system. So basically anything outside our interested region is surrounding. So if we take our cube as the system boundary, like here, so anything outside is going to be our surrounding. So if we consider our balloon surface as our system boundary, anything outside that is going to be our surrounding. So in the case of building, outer atmosphere is our surrounding. Okay, so the definition of boundary, the real or imaginary surface that separates the system from its surroundings. Right, now you can see it's not necessarily a real or physical boundary. It can be an imaginary one, as we discussed with the cube, right? So I believe we are clear about system and surroundings and how to define a boundary. And any questions on that one? Or are we perfectly getting it as of now? Are we good? Perfect. Now, so we'll look into the concepts of isolated system, closed system, and open system, right? So you remember we discussed this in a previous slide to get your brain working on this one. So if we think of your thermos, right? So let's say this one, right? And with your thermos, like it keeps the heat of a substance. If you put in if it maintains the temperature, if you put in cold beverage inside, then it will be maintained in a cold temperature. If you put a coffee inside, then it will be a hot coffee when you consume it in a later time. So once you put, let's assume that you walk into a Tim Hortons, not under the pandemic situation, but in a general setup, and they had the process to bring your own cup kind of a thing, right? So like you take your thermos and give it to the salesperson there and ask, okay, please put some coffee in here. So he or she put coffee and then you get it and the lid is closed. Now can the coffee leave the thermos? It cannot, right? And can the heat leave the thermos? It cannot, right? So if it is properly insulated, then it cannot heat cannot leave the thermos as well. So basically now heat or mass is not allowed to go outside, right? So there it's an isolated system. So the definition is no mass and energy can cross the boundary, right? So with a closed system, let's assume like you go to Tim Hortons again. You can do it now as well. So you go to Tim Hortons and you buy a coffee and they put up the lid, right? So now it's sealed. Let's assume that it properly seals, but usually when you put up a Tim Hortons coffee upside down, then it's likely to get rid of the lid and coffee will likely fall down. But let's assume that does not happen and now the lid is closed, right? So now what do you think? It's a closed system or isolated system? Any ideas? It's a closed system. It's not exactly an isolated system. Why? Because the coffee cup Tim Hortons provide is not insulated. That's why you can feel the temperature outside, right? If you do not get a sleeve, sometimes it can be too hot for your palm as well, right? So now we can call that a closed system. And if you take that coffee cup and now you want to drink the coffee, right? You cannot obviously drink coffee from a closed system, because in closed systems the mass is not allowed to transfer. If you want to make it, if you want to drink it, so you want to make it an open system. That's why you turn on that small nipple kind of cap and then you drink it, or like you can remove the entire lid and then drink it, right? So in that case it allows the mass transfer, because that's why we consume coffee, that's how we consume coffee. And at the same time still you can feel the heat, and not only the heat, with the mass going out, the energy is also going out, right? Because the thermal energy contained in coffee is also going into our body while we consume the coffee. So it's an open system. So the definition of an open system is a selected region in space or mass, and where mass and energy can cross its boundary, right? So what is this control surface? So in control surface, because if we draw our coffee cup like this, and it's inside it we have coffee, and we need to like define a system boundary, and certain cases like we don't have a physical boundary, like this becomes our control surface, right? Or imaginary system boundary. Okay, are we clear on that? Perfect. How is mass can go out in open system? So basically open system is a coffee cup. Let's take the example of coffee cup, a coffee cup without the lid. Basically if you like when you drink it, so the coffee can go into your mouth, right? So it has an opening or some way to send mass in and out. Are we clear now? Okay, perfect. Okay, now I want you to try to find whether how can we simulate these processes as an open system, closed system, or isolated system. You can pick 1, 2, 3, 4, and then like put like open, closed, or isolated under each number and put it in the chat. Take 1 minute if you need and put it in the chat. Once you have decided, put that in the chat. Okay, we have two answers which are essentially the same thing, and I think you nailed it. The first one is a closed system, because if you think of a soda can that you take out of your refrigerator, then you will feel the cold of the can inside, right? So it's not insulated, so the heat or thermal energy can cross the boundary, and at the same time if you do not open it, like the mass cannot cross the boundary. So it's, we can model it as a closed system. And the second one is a condensing unit of an air conditioner, right, placed outside your house, right? And that one, there you see the cold air or hot air coming into the system, and at the same out from the outside surrounding, right? And again, in addition to that, we have the refrigerant from inside the house flowing through the coils of the air conditioner. So again, the mass can transfer, and obviously if the heat cannot transfer in a condenser, then this, we cannot call it a condenser, right? So we use condensers to cool refrigerants or some substance. So that way you can see it can be modeled as an open system. And if you look at the third image, it's a sealed and well insulated. So sealed, we get the clue, the mass cannot transfer, that's why we seal it, right? And then it says well insulated, insulated in the sense then the heat cannot cross the boundary. So now we see, okay, no mass, no heat, then it's an isolated system, right? The pipe, a pipe section, a well insulated pipe section. So this could be confusing at times. When you say well insulated, you feel okay, now it's insulated, no heat can cross the boundary of the pipe. It's true, but it's important to note the water coming from one end to the other, water can leave, right? If we take a pipe section like this, water enters and leaves continuously, right, when it's underwork. Like if it is insulated like this, the heat cannot transfer through this surface. So we can say that there's no heat transfer here, but both heat and mass can enter and exit the pipe from these two ends. So it's an open system. And you can see if the pipe was not insulated, it would not change the condition of open or isolated or whatsoever. If it was not insulated, the only difference would be the Q here would not be zero, right? So it would not be zero. So are we clear about that? Anybody having any doubts or questions? Perfect. So let's take 10-minute break. That will be nice to have a break and refresh yourself, have a coffee, and then let's all meet at 9:15 to continue the lecture. Hello, are we all back? Awesome. So is the pace of the lecture good? Like it's in an understandable manner? Like anything that we can improve? Perfect. Thank you. Okay, assuming that all of you are here, let's continue with the lecture. So the next thing is the continuum approach, right? So how we analyze a system. Do we go into the molecular level, or like do we consider the entire space and consider how the space work, right? So to give you some context about this matter, I will take the example of city of Kelowna. If the city of Kelowna want to develop a plan, would the city of Kelowna would go to like individual person and ask the question, or like think everybody in the city as a continuum or like a system and try to come up with the solution? Let's say they want to develop incentives for energy efficiency upgrades, as the Fortis BC and everybody doing right now. So in such a thing, would they come to each and every person, myself and each of you, and like try to plan it according to ourselves, or like think of the city as a whole and plan that? They will treat the city as a system, right? Like not individual people, like, but without focusing on individual persons, like they will think the entire population and try to come up with plans. So if you want to hire somebody for a given position in city of Kelowna, what would they do? Like think of the population and say somebody from the population come to the vacancy, or they will individually interview the candidates? So they will definitely individually interview the candidates, right? So in that case, you can see, depending on the context of analysis, we choose whether we need to go in a high level, or like we want to go into the particulate level, like to individual people, persons level. So the same idea applies for thermodynamics as well. So if we are interested in one particle, like what happens, how the trajectory of that particle happens, and in a given fluid flow, what is the velocity at a given point, that what we do with computational fluid dynamics and stuff. So it's a different study. So we can identify and evaluate particulate level. But in classical thermodynamics, or in the context of this course, not in classical thermodynamics, in the context of this course, what we are interested in is the city level planning. So basically, the space, and we are not interested in one water molecule, rather, we would be interested in what happens to water when we heat it up, right? So therefore, we apply the continuum approach for this analysis. So I will go through the definition. A system of a fluid is made up of a large number of colliding molecules. So this is how a fluid can be defined, right? Large number of colliding molecules. Okay, a fluid is treated as a continuous substance as opposed to a collection of discrete molecules. So you remember the example of the city. So now we do not think of the city as like collection of individuals and try to customize our plan to individuals. Rather, we say that uh, this city is a like collection of individuals and like other surroundings, and it's a continuous system, right? And continuum is valid as long as the size of a system is large enough to comparison to the distance between molecules. So let's say if we have molecules of this size, and obviously molecules are going to be very smaller than this, but let's say for argument's sake, we'll take this is the size of a molecule. And compared to this size, if you think the box that I'm doing the video right now, so like this box, like, right? So like this entire boundary, oh, I don't know where to put, okay, this boundary, right? So compared to that, this is very small, right? In such a situation, we can say that we can analyze that system using a continuum approach. Let's say the particles in the system, let's say system boundary is the boundary of the video, and the particles of the system are the size of my head, right? So then we cannot use the continuum approach because my head is a significant size compared to the system boundary. Therefore, we have to be careful, but in all the analysis that we have in this course, we will have particle sizes very small compared to the system boundary. So without a doubt, you can use continuum approach to analyze this kind of systems that we encounter in the coming sections of the course, right? So now we come to another important aspect of thermodynamics: properties of a system, right? You all know that when we look into a system, thermodynamic system, there's pressure, temperature, volume, mass, internal energy, and there's some other new terms like internal energy, enthalpy, entropy, right? Pressure, temperature, volume, mass. Like all these terms, I am pretty sure that you have used somewhere else in other courses or in your high school. But some of you may not be familiar, or maybe all of you may not be familiar with internal energy, enthalpy, and entropy, unless you did some reading by your own. So these three parameters, I will leave it aside for now, but we'll discuss these parameters in the coming lectures. Okay. So it's true that we have different properties. At the same time, we can categorize these properties into two types. The first one is extensive properties. The other one is the intensive properties. Okay, let's try to see what's extensive property. In an extensive property, it's dependent, that property depends on the mass of the system, right? So you can see here there's a figure. So if we take this one, and once we divide it into two, if that property depends on mass, then it has to change its value, right? So looking at this one, you can see when we divide this into two sections, the mass divides into two, the volume divides into two, but temperature, pressure, and density does not change its value, right? If we take a full water beaker and put half of that beaker into another beaker, and now we have two beakers filled with water, right? So it's what we have done here in this figure as well. So there the mass divides into two, water divides into two, but temperature, pressure, and density, they did not change. So let's see. Now the mass and volume fit the first definition, right? Depend on the mass, right? So like when we divide the mass into two, the obviously mass divides into two, and then volume divides into two. Therefore, they can be called as extensive properties, but we cannot call temperature, pressure, and density extensive. Let's see whether it fits the intensive property definition. Intensive properties are independent of the mass of a system. Now, which means if we divide the system into two, these properties does not change its value, right? So now temperature, pressure, and density are intensive properties. Okay, and another tricky thing that could come into play in a question, I might ask whether specific volume is an intensive property or extensive property, right? Specific volume is volume per given mass or volume per unit mass, right? Specific volume can be written as volume of a given substance divided by mass of the given substance. So can anybody say whether a specific volume an intensive property or extensive property? Intensive property or extensive property? Okay, we have one idea, extensive property. Okay, any other ideas? Okay, now we have both. Okay, let's see. Okay, let's assume the specific volume, right, of this given system. Let's call this system 1, and it's definitely V divided by M of the system. Let's put it here. Specific volume 1 equals V divided by M, right? And let's call this one system 2, like this half of the system. And that is going to be V2 equals the volume is total volume of the previous system divided by 2 and mass of the previous system divided by 2. So essentially it becomes V divided by M. So now you can see it does not, specific volume does not change its value even if we divide the system into two, right? So then what can we call it? An intensive property. Are we clear on that one? Anybody having doubt? Not clear? Okay. So so Kylie, the idea of intensive properties is that it should not change its value once we divide the system into two, right? It is independent of the mass of the system, right? So the mass of system 1 is M, and for system 1 we determine that this is the specific volume, V over M, right? So the total volume is V and total mass M, so we determine the specific volume to be V over M. And now we try to calculate the specific volume of system 2, and like now we have three systems, right? Because we divide system 1 into two sections so that each have half of the mass of that substance. And now the new volume, new total volume of system 2 is V over 2. Do you agree with that? V over 2? Kali, are you there? Okay. So now, do you agree that the new mass is M over 2? Perfect. Now we try to calculate the specific volume, and we substitute V over 2 as the volume and M over 2 as the mass. And once we do that, like these things cancel out, right? So we end up having V over M, which is same as V1. So basically what that means is the specific volume did not change even after dividing the mass into 2, right? So according to definition, if a property is independent of the mass of a system, that is an intensive property. Are we clear? Perfect. So any other questions on that one? Okay, so similar to this one, it's very important. You should remember any specific property is intensive. So if it is any property you don't know, internal energy, internal energy is not specific intensive property, but specific internal energy is an intensive property. Are we clear? Volume is extensive, specific volume is intensive. Enthalpy is extensive, specific enthalpy is intensive. Entropy is extensive, specific entropy is intensive. Did I make it clear for everyone? I hope we did. And if you have any questions, feel free to put it in the chat so that we can discuss. Okay. So equilibrium. This is another important aspect of the course. So equilibrium, a condition of balance. In an equilibrium state, there are no unbalanced potentials or driving forces within the system, right? So if I hold this pen like this, okay, if I hold this one here, then you can see this pen is not moving anywhere. That means the forces acting upon the pen is balanced. That's why it stays in the same point. If it has an unbalanced force, then it will start propagating like this, right? Like this, somewhere, right? In one direction. So we know this physical equilibrium, right? The force balance. So we'll try to see what are the other useful equilibrium definitions that we need to know in this course. So the first one, thermal equilibrium. Same temperature throughout the system, right? If a system is in thermal equilibrium, then it should be the same temperature throughout the entire system. If we take our coffee cup example, then if we say that the coffee cup is in thermal equilibrium, the coffee on top and coffee in the bottom and coffee in the middle, everything should have the same temperature, right? So if the temperature across the coffee cup changes, it's not in thermal equilibrium. So as we all know, in our body, the temperature changes, right? In certain parts, when we think too hard, sometimes our head gets heated up a little. I mean, literally, right? The temperature of the head goes a little higher. So maybe our hand is not as heated. So in such a situation, our body is not in thermal equilibrium because we have two different temperatures at 2 points, right? So that is thermal equilibrium. And mechanical equilibrium, what is that? No exchange in pressure at any point of the system with time, right? No change in pressure. So if we take the coffee cup again, the pressure of a given point does not change from one point to the other, one point to the other, right? So it is in mechanical equilibrium. With time, if the pressure does not change, then it is in mechanical equilibrium. Obviously, if we draw the coffee cup like this, and pressure from this point to this point will change, but with time it would not change. Like t equals 0, t equals 1, sorry, t equals 1. Again, every time the pressure at this point will be the same. Okay. Phase equilibrium. The mass of each phase reaches an equilibrium level and doesn't change with time. Okay. If you think of the coffee cup example, Now we have the lid on with this coffee cup, right? And now it's a closed system, and we have coffee vapor here, some water vapor or coffee vapor, something, right here, and we have coffee here, liquid, right? Now if it is in equilibrium, uh, it would not change the volume of vapor and liquid with time. So if it is not in equilibrium, now this is the original coffee level, and maybe it will end up being here and more coffee vapor will be there if it is not in equilibrium. Once it finds the equilibrium level, the amount of coffee vapor and amount of coffee liquid would not change. Am I clear on that one? This vapor equilibrium could be challenging. If you understand it well, that's good. Perfect. So the other one is chemical equilibrium. So no chemical reactions occur in the system. So you put some stuff together and then it does not react with each other, then we can say that it's in chemical equilibrium. Certain chemicals cannot be mixed together because it reacts and then it is like creating some fumes and whatnot, and maybe after some times it reaches a equilibrium state where they do not react with each other anymore because maybe they have done reacting, right? So at that point we say that the system is in chemical equilibrium, and obviously there are certain things are already in chemical equilibrium because they do not react with each other, like sand and sugar. Mix that and you wouldn't see much of a reaction there, right? So compared to chemical equilibrium, the other three equilibriums will be frequently used in our course. So chemical equilibrium is important, but not for the calculations in this course, right? Okay, moving on. Now this is one of the important concepts for your calculations: state, process, and cycles. You will be drawing, marking the states and drawing the processes and drawing the cycles and calculating the work done, heat transfer, and whatnot during these cycles and processes. So this understanding is very important, right? So state, condition of a system described by a unique set of properties, right? Let's say in this figure here, this is a state. 1 is a state and 2 is a state, because we can define that using temperature, pressure, volume, and other thermodynamic properties. Okay, how many properties are needed to define a state? We'll discuss this in the coming lectures, right? So for now, you know that using thermodynamic properties, you can define a state. And if I mark a point here, you can call it 3. Is that a state as well? It is, because any point in this PV diagram can be called a state, right? This is a state 2, and this is a state 2. Any point. So it represents a given set of properties that represent a given condition of a substance, right? So are we clear with the state? I'm sorry I asked this question a lot because the basic concepts, if we miss that, that's kind of confusing at the end. Are we clear? Perfect. So process, the next important aspect of a thermodynamic and assessment is a process. We can call it a change that a system undergoes from one state to another. The initial and final states and the path must be specified to describe a process, right? So now, looking at the definition, can you say that the green line, is it a process? Yes, it is, because let's check from one point to another of the definition? Does it mark the initial and final position of the process? Yes, there are two states and it is being marked here, so it's clear. And the path, does it have the path? Yes, it marked the path. And does it describe the direction? Yes, it described the direction. Now we can say that it all this drawing meets the definition of a process, so we can call it a process, right? Now the third one is a system, a cycle. A system completes a cycle when it returns to its initial state after undergoing a number of processes. Okay, so if I draw, like now we have one process, and like if I draw a process that connects with the state 1, right, comes back to state 1. Now can we call this a cycle? Can we call this a cycle? Perfect. We can call this a cycle because the definition requires us to come back to the original or initial state, right? Once the system reaches the initial state, then we can call it a cycle. So if we have, okay, now if I draw the same process coming back like this, can we call this a cycle? Now we reach state 1 again. Can we call this a cycle? Perfect. Still it does. Irrespective of the path, if we come to the initial state after completing a set of processes, then we call it a cycle, right? So this is very important. Like the cycles are very important. The refrigeration cycle, internal combustion cycle, and like Rankine cycle. Like there are many thermodynamic cycles that are useful for our day-to-day applications in designing engineering devices. So it's very important, right? Do we have any confusions here? I hope not. If you have, like, you can put it in the chat. Okay. So equilibrium state, you remember we defined 4 equilibrium states, right? So we only deal with systems in equilibrium states, right? So if we do not use the equilibrium states, let's see what happens, right? Here the second point says quasi-equilibrium process. It defines a process as quasi-equilibrium process. What is a quasi-equilibrium process? When a process proceeds in such a manner that the system remains infinitesimally close to an equilibrium state at all times, then we call it a quasi-equilibrium state. Okay, now I'm if I were in this lecture, listen to me, it looks like something not clear, right? So let's think of a piston cylinder mechanism as shown here in the figure, and we try to push the piston, right? Once we start pushing the piston, then it presses the closest particles, and then the pressure build up here, pressurize the particles here, and then this front pressurize the particle here, right? And once this happens, like the temperature of this point can change, and this temperature difference create a temperature difference at the second point and second wavefront, and it continues propagating like this, right? So if I push the piston like this very fast, and then it hits the particle immediately, comes to the surface, and then it pressurizes that and it compresses that small tiny block of air or whatsoever the substance, and then that block transfers that to the other block and keep on going, right? So if we try to draw a PV diagram for that, like you can see here in this block, we have drawn a PV diagram. So let's say the pressure of this point at a given point is going to be this, let's say P1. And can we say that P2 and P1 is equal to each other? Can we say, if we do it real fast, and is it equal? It is not equal, right? So because, as I mentioned, if it is happening too fast, then the pressure, then the pressure builds up, right? And then it goes on. And similarly, if you do it too fast, with the pressure change in one block of substance, as this block, the temperature can raise, right? And it might not be necessarily the temperature raise that we observe here, because it's a different pressure and different set of properties. So now, to represent this state, you see that we have to use multiple pressure values if we are to represent this state here, and we have different pressure values, right? So for a given volume, we have different pressure values. And similarly, if you come to another point, then again, multiple pressure points like this. Like definitely we cannot draw a process line, because if you want to draw a process line like this that you see in the figure in green color, then we should have one state, right? So, but in such a situation, if we move the piston very slowly so that the system comes at an equilibrium state, now we take one step and we allow time for all the particles to enter the same pressure. Now, can we draw the pressure and volume? Can we represent the pressure and volume of this process using one dot like this? In such a situation, if we do it infinitely small steps and slow, can we do that? Can we use one point to represent this process? I will answer the questions after going through this discussion, right? Otherwise it disrupts the flow. Anybody, any idea? We can, right? Because like we allow it to arrive at the equilibrium. Otherwise, if we do it too fast, like we apply pressure and the first particle set collide with the surface, get pressurized, and then the other particles have some different pressures, and still like we are not stopping and we are not allowing the system to enter the equilibrium state, we push it again, and likewise we keep on going, right? So at each piston point we have multiple pressure values, temperature values, and etc. inside the system, right? So if we allow it to enter to equilibrium state, then we can represent the entire system using one value for pressure, temperature, and specific volume and other properties. No, like the thing is, the pressure change, like with time, it is confusing, right? In pressure equilibrium, pressure at a given point should not change with time. So let's say if we apply the force too fast, and now we have a pressure front here and a different pressure values here and another value here, right? So if we allow the system to stay, does it change the pressure at a given point? Like let's say A, B, and C. Does it change? It changes because like we applied the pressure and the particles collide with each other with the surface, then it increased the pressure, but the adjacent particles were not as pressurized, and then it changes, right? Because now like we stop the piston at a given point, still the point A has a different pressure, point B has a different pressure, point C has a different pressure. So it will change until all the volume comes into one pressure. Do we agree? Yeah. So that's why if it is in pressure equilibrium, then it would not change with time, the pressure at a given point, right? So if we allow enough time for the system to set its pressure to the same value and temperature, and so that it is in equilibrium, thermal equilibrium, mechanical equilibrium, and everything, so then we have a uniformly distributed pressure and temperature set of numbers. Are we clear? Perfect. So that's why we use quasi-equilibrium processes to represent our thermodynamic processes in this analysis, so that we can evaluate the states using one state point. And if we want more accuracy, like depending on the thing, right? If you want more accuracy, you can analyze the system with transient variations. So which means with time, the property can change. We have to consider that. So the transient system analysis is not something we do like in this case, right? So we assume the systems to operate in a state under steady conditions, and also we assume the processes that we use in this course are to be quasi-equilibrium processes. Okay. So when we say that, I always used to think, okay, more accuracy is better, and like sometimes I mean, the things becoming more complex means it's more fancier kind of thing, but it's not always true. For an example, if I take the example of the city of Kelowna, if somebody comes there and say, okay, I need to develop a financial incentives plan for energy upgrades, and I go to individual person and say, okay, what is your need and what not, and then I ask the question from everybody and try to take the decision, it will take me years, and at the same time it will take me more effort, but sometimes the improvement is not significant compared to the effort that we put. So in such a situation, we do not try that approach. So the same thing applies. Engineering is always about compromises, right? So when you machine a shaft, you can go to the most precise shaft, like 0.001 millimeter tolerance, right? So you can do that. You might feel better, but your company might not feel better, because to machine that accuracy, you need to get precise equipment, and you need to pay more, and the finances of that product that you develop will not be there. So similarly, in thermodynamic analysis, in certain cases, the high level analysis is enough. At the design stage, we just need to see, okay, this process happened, that process happened, and this is the efficiency, this is a theoretical maximum. We just need to see whether we want to go ahead with this process and investigate further or not. You know, in engineering, like we have something similar like pre-project planning. So in pre-project planning stage, we don't design the entire bridge or entire building or entire engine or the entire ship just to say, okay, this is not a feasible project. So you do some basic calculations, the basic finances, basic design calculations, and see, okay, whether this is a feasible process. Okay, so I'm trying to give you some context why we need this high level analysis and also specific analysis. So like both are needed at some stage of a decision making process related to engineering. Okay, so now we discussed about a cycle, right? So we said when a process goes through a cycle and reaches its original state after a while, then we can call it a cycle, right? Now I'm pretty sure that you have seen your refrigerator, right? So in your kitchen. So if you have seen this one, did you know that this follows a cyclic thermodynamic process, right? the refrigerator you have in your house, it follows a cyclic refrigeration process. It follows the refrigeration cycle, to be clear. So if we look at the schematic here, this one shows the process that it follows. So first, we have the evaporator. So evaporator absorbs heat from the refrigerated space. So inside your refrigerator, you feel it's cold, irrespective whether it's hot outside or whether it's cold outside. The refrigerator is anyway maintaining the temperature it's is supposed to be, right? So now the evaporator absorbs energy from the refrigerated space. So when the energy level of the refrigerated space drops down, the temperature drops down. So which is what we expect from a refrigerator. And then after absorbing the energy from the refrigerated space, the refrigerant evaporates. We call the fluid that is running through this cycle the refrigerant. So refrigerant evaporates, and evaporated refrigerant comes to the compressor, and there we compress the refrigerant and increase the temperature of the refrigerant. With that, we send it to the condenser. So with the higher temperature of the fluid now, it can eject that heat or dissipate that heat into the surrounding, so which is our kitchen area or living area, wherever our refrigerator is placed at. And after doing that, now it drops the temperature because it removed some energy from the refrigerant at the condenser. And now after that, it enters the expansion valve and it drops the pressure further. The pressure of the refrigerant is further dropped at the expansion valve. Now it comes to the initial point and the cycle continues. Okay, so here in this pH diagram in the right hand corner, you see the thermodynamic process. We started at point 4 and we went around the entire cycle and came to the initial state. So it matches the definition of a cycle. So we will not be discussing how this pH pH diagram was drawn at this point, but definitely we will be discussing this one in the coming lectures. Okay. Okay. Now we come to another important property of the thermodynamics assessments, and the first one is the density. I'm pretty sure most of you have already heard the density. So density is the mass per unit volume. So if you want to find the density of a given substance, then you can take the mass of the substance and the total volume of the substance, and then you can divide each other and then find the density. So it's very important to note for gases, the density is density depends on temperature and pressure. So if we have a gas and then if we heat it up, then the density changes. If we pressurize it, then the density changes, right? So if you remember that we had ideal gas law as PV equals mRT, and if we divide both sides by the volume, and then it becomes PV equals M over V RT, RT, and which is rho RT. So pressure can be written as P equals rho RT from the ideal gas law. That is what we see here, right? For liquids, it's slightly different. So the density changes with temperature, but not with the pressure. So if you remember the last time you bought a pop bottle, which is full up to the lid, and then if you try to press it so hard, still the volume would not change significantly, right? So if you have not already done it, you can take an empty pop bottle and fill it up with the water up to the lid and try to press it and see whether the volume changes. Okay, Desa, you can go ahead. let's say you raise the hand. Do you have a question? Oh, PV equals nRT. So this is the gas constant that we have here. So if we used PV equals nRT, so that is going to be universal gas constant. So the only difference, you see here is the difference between the gas constant and the universal gas constant. Gas constant is R, and R over M is universal gas constant. So I'm not going to do the derivation here, but if you want the derivation, I can explain you in detail after the class. But if you use Ru, then you use the number of molecules. But if you use gas constant, which is R, then you can use the mass of the substance or gas. Did I answer you, Desa? Perfect. So back to the discussion. So as I mentioned, if you fill up the pop bottle with water up to the lid and try to press it, it doesn't really change the volume. But if you put it in your freezer, then after a while you'll see that it bulges, or either it may like break off, and still the volume will be expanded, right? So it is something to note. With temperature, the density of a liquid changes, but with pressure, the volume change or density change is negligible. So are we clear with that one? So this is a very important observation that we will use in the coming calculations for thermodynamic processes. When you use tables, you use this quality or this trait of liquids to find thermodynamic properties when you have limited information, right? So with pressure, again, the density does not change, the specific volume does not change, but with temperature it does, okay? And the specific volume is essentially can be written as 1 over density. So it is the volume per unit mass. The definition is the upside down, right? And throughout this course, we'll be using SI units. So wherever you see density or specific volume, you are safe to use kilograms per cubic meters or cubic meters per kilogram for the specific volume, right? For density, kilograms per cubic meter. So now I have a question for you. From the knowledge you have from the previous discussions, are density and specific volume intensive or extensive properties? Density, is it intensive or extensive? Anybody? Any idea? Density is intensive, right? So if I do the same exercise I did for the last time, so let's assume the M and V for system 1 and we divide it into two cases, and for system 2, M divided by 2, V divided by 2. You can see density is M over V. So for the system 2, we divided by 2, and then again it is equal to rho 1, right? So basically, Nathan, your question is right. So specific properties are always intensive properties, okay? So density is also a specific property, right? Awesome. Now moving on to the next one, pressure. So pressure is a scalar quantity. So you can find the pressure of a given gas or substance, and pressure at any point in the fluid is the same in all directions. So if you take one particle, the pressure in all directions from that particle, it is the same, right? At a given point, then from that point, the pressure that is going outwards or coming inwards, like that is the same value. But it's very important to know now this is a scalar, right? Because this has no direction. It is what it says. But pressure force is a vector, right? So if we have something submerged in a water tank, the pressure acting upon this surface, let's assume the pressure at PA is PA, and the force is FA equals PA into the area, right? So that force has a direction. It's a vector, right? So, and the other important thing is the pressure force is always normal to the contact surface. So if the submerged surface is this one, and if I want to find the pressure force acting upon this one, and it is always normal to this one, perpendicular to this surface, contact surface, right? And then we have absolute pressure, which is true pressure at a given point, right? So if you say, like, when we want to say our age, like we can tell it compared to somebody else. I can say that I am 5 years older than some person, and I am 3 years older than some person, right? That is a relative scale. Okay, compared to that person, I am this many years old. Or I can say I am 30 years old, 32 years old, something, right? So that is like from my birth date to now. So that is my absolute age. And if I explain my age compared to that one, that is similar to gauge pressure. So I explain it compared to a known benchmark. So if you all know the age of one of your friends, I can say that compared to that friend, I am 10 years old, something like that, right? So the gauge pressure or vacuum pressure is given relative to the atmospheric pressure. Compared to your friend, in the case of age, we give gauge pressure compared to the atmospheric pressure. Compared to the atmospheric pressure, it is 10 kilopascal higher. So the gauge pressure is going to be 10 kilopascal in that case. But the absolute pressure is going to be atmospheric pressure plus 10 kilopascals, right? So in most thermodynamic investigations, we use absolute pressure. So especially when we look into the thermodynamic property tables, we don't use gauge pressure to read thermodynamic property tables in most cases. Like in this course, at least, we don't use gauge pressure. So do we have any questions? Are we absolutely clear about this one? Gauge pressure and absolute pressure? Perfect. And now we have temperature scales. You know, when we want to define a distance measure, let's say 1 kilometer, right? We can mark one point maybe in front of EME building in UBCO, and then we can go certain distance and mark another point, and we can say, okay, we'll all agree this is 1 kilometer, right? And then if we replicate that in another place, that distance, then we'll get 1 kilometer again, right? So that is to measure distance. But in thermodynamic cases, when it comes to temperature, we cannot necessarily see such physical stop point and start point. Therefore, we use some known physical phenomena, ice point and steam point, to define temperature scales. What is ice point? The temperature of a mixture of ice and water that is in equilibrium with saturated air at 1 atm pressure, right? So if we take a water basket and we see that ice cubes and water is in equilibrium and the pressure is 1 atm, then we can call it the ice point, right? And steam point is when you see the steam coming out, and then this steam and liquid water is in equilibrium, right? You know, the phase equilibrium. the amount of vapor or amount of liquid should not change. The amount of substance in each phase should be in equilibrium. And if the pressure of that system is 1 atm, then we call it steam point. So now you have something you can replicate at UBC or UBC Vancouver or somewhere else in the world. If you maintain 1 atm pressure, and if you see that water, liquid water and steam are in equilibrium, then you can say that steam point. Similarly, you can replicate the ice point as well. So when we defining Celsius scale, we say that ice point is 0 Celsius and steam point is 100 Celsius. Okay, so we have 100 equal divisions, which we call Celsius. And when we are defining Fahrenheit scale, we say that ice point is 32 Fahrenheit and steam point is 212 Fahrenheit. So at ice point, the Fahrenheit reading is 32. At steam point, it is 212. And between these 2 points, we have 180 equal divisions, right? So these are just agreements that we make. Okay, like we'll divide this scale into this many, and so that somebody else can again at some point can tell, okay, this is the temperature that we all understand, right? And in this course, like throughout this course, we'll be using Celsius and Kelvin, the SI unit system. We'll not be dealing with Fahrenheit in this course. Okay, so in Celsius scale, we already defined at ice point temperature is 0 Celsius. At steam point, temperature is 100 Celsius. So if we want to find the Kelvin reading at a given temperature, what we need to do is we just need to take the Celsius reading, and add 273.15. So basically, let's say somebody says the temperature at this point is 30 Celsius, and we need to know the Kelvin reading of that one. And then there we can say 30 plus 273, which is 303.15, is the Kelvin reading. So if it is 30 Celsius in Celsius scale, that is 303.15 in Kelvin scale. Are we clear about that one? Perfect. So that is the theory part for today's class. Now we'll quickly jump in to a few examples to see whether we understood some of the basic concepts, right? So try to solve this one in about 2 minutes. We'll discuss the solution. So please take out a paper and work it on, and or in your tablet. Please work out these examples in the class so that you get the questions as much as possible. For those of who you are trying to do this, so it has a tank with 2 compartments, which is divided by a membrane like this. Oops. Membrane. And the volumes and other information of these chambers are given, and it asks when the membrane is broken, what is the final density of air? Before the membrane was broken, the temp A and B had different properties, and now we break the membrane so that everything inside the chamber is mixed. If you get the answer, please put it in the chat. 1.28. Yes, it is the correct answer. Well done, George. And so let's try to solve this together, right? So if we want to find the final density, so we want to let's say the final density is rho final. So rho final should be m total divided by v total, right? So now we know that once the membrane is broken, the total mass of the chamber is the sum of MA and MB, and total volume of the chamber is going to be VA plus VB. So if we know M total and V total, it's a piece of cake to calculate the density. But we need to know MA, VA, and MB and VB. So in the question, it says room A has 1 kilogram. So MA is known, and the air volume is 0.5 cubic meters inside the same chamber. So MA and VA are given. So it's very straightforward in that case. But in room B, we have been provided with volume and density. So in order for us to find the mass, we have to use the definition of density. So definition of density is rho is equal to m divided by v. If we want to find the mass, then what we can do is we multiply the volume by density. Now we substitute 0.75 cubic meters here, and then 0.8 kilograms per cubic meter is the density. So we get MB, and VB is already given, so 0.75. Now we can find M total, which is 1 plus 0.6, 1.6 kilograms, and V total 0.5 plus 0.75, 1.25, and we get the ratio and we find the final density. Does anybody feel anything challenging about this question? Anything not clear? Or are we all good? Perfect. Now let's go for another example real quick. And once you find the answer, please put it in the chat. So in this case, we have a piston cylinder mechanism and some weight is placed on this one, and the total weight of the piston and this thing together is given to be 100 kilograms, right? And the atmospheric pressure is given as well, and the question asks absolute pressure inside the chamber. Pressure inside the chamber. Please let me know once you got the answer. Okay, so I will quickly explain this one. I think Desa got close to the answer, 156 kilopascals. So let's all go through the solution together. So the gas inside the piston creates some pressure, and it creates a pressure force upwards, and then the atmospheric pressure outside the system, like it creates a downward pressure on the piston as well, and then the weight acting upon the piston, that creates a W, or W equals mg weight, right? So if we consider the force balance of the system upwards, so the upward forces are Pg into A, the gas pressure, into the area of the piston cylinder, and there's no any more upward forces, and then P naught is the atmospheric pressure, and the pressure forced by the atmospheric pressure is acting downwards, and also the weight of the other things, the weight of the piston and the weights are acting downwards. So we can write the force balance equation like this, and then we can write Pg is equal to P naught plus mg over the area of the piston cylinder, right? So atmospheric pressure is given in the question, and m is given. Gravity we can assume 9.81, the acceleration, gravitational acceleration, and the diameter of the piston is given, so we can convert it into the meters. It's very important. Always try to stick to the standard SI units. so that you don't end up getting confused, because you can substitute centimeters here, it's not a problem. But if you substitute in meters, you straight away get the other standard unit for pressure, like I mean Pascal, right? If you substitute in centimeters, then you will have to do some conversions down in the road. So I personally like to substitute in a standard SI unit so that we get the same number, same standard units in the answer. So once we substitute everything, we can determine that the pressure is this one, and we can say that it's 156 and 838 pascals, or 156.8 kilopascals. Anything not clear about this one? Okay, I believe it is clear for everybody. So multiply P by area. So pressure is the force acting per unit area, right? So if we want to calculate the force is not the force per unit area, force is given by newtons, right? So in order for us to determine the total force, we have to multiply the pressure applied on that surface by the total area. Did I answer you, Minna? Okay. So the next two questions I will not discuss today. So like you can try it at home. The solution is there for the question 3, and question 4 is almost same as what we did in the previous questions. From that knowledge, you can do that. And if you have any challenges with that, we'll discuss these two questions after the class tomorrow, not during the class, after the class. Okay.